Alright guys, today what we're going to talk about are precipitation reactions. Precipitation reactions. And this is the third of the three solution reactions that we've been talking about. And what happens in this reaction is you mix two soluble products and you get an insoluble product, or a solid to come crashing out of solution. So a solid forms when two aqueous solutions are mixed. And what comes out of this is what's known as a precipitate, or an insoluble product. So one that comes crashing out of solution. So what about soluble products? What happens there? So let's consider a soluble ionic compound. And what happens when we toss these in solution? And we've somewhat talked about this when we discussed acid-base reactions and even redox reactions. So let's talk about soluble ionic compounds. And ionic compounds that dissolve in solution are considered soluble. They go into the salt. So ionic compounds that dissolve in solution are considered soluble. So they go into solution. Well, how does this happen? Well, if we have an ionic compound, we have a cation and we have an anion. Cation positively charged, anion negatively charged. And then once they go into solution, they're hydrated, where water molecules surround these ions. So when they surround these ions, that's when it's considered hydrated. So what happens is the water molecules come, they break apart the solid, and you get soluble anions and cations. So, water molecules coordinate or surround the anions and the cations of the salt or the ionic compound, and this is known as hydration. So if we go to draw this out, let's say we have a cation and we have an anion. Well, let's consider water molecules coordinating to these. So if we look at our cation, which is positively charged, and we consider the Lewis dot structure of water, we know that there's an overall dipole moment pointing in this direction, and there's a partial negative on the oxygen and a partial positive on the hydrogens. So knowing that, the oxygens, which are partially negative, should be more attracted to the cation. So if we draw kind of water molecules coordinating this, there's going to be somewhat of an interaction this way. And when we discussed supramolecular or intermolecular attraction forces, we gave this interaction a special name. And this interaction is known as an ion-dipole interaction. OH. There we go. Now, let's say we consider water coordinating to an anion, or a negatively charged particle. Which direction will point towards it? Well, whichever one is positively charged or partially positively charged. In this case, it's the hydrogen atoms. So There's an attraction between each hydrogen atom to that anion. And even though I'm only drawing 4 water molecules, depending on the size of the anion or the cation, you may have more or less water molecules coordinating for the system. All right, so in an aqueous solution, an ionic compound, as I said, dissociates into anions and cations. Let's see an example of this. Let's consider some salts that we've named in the past. So, an aqueous solution solutions, if soluble ionic compounds split into anions and cations. Hydrated ions. So those water molecules coordinate to those ions. Example, if we consider sodium chloride in an aqueous solution, we can really think of it as solubilized sodium ions that have a +1 charge from our oxidation state rules, aqueous, and chlorine anions that have a -1 charge, which again we know from our oxidation state rules. Let's consider magnesium chloride, which we looked at for one example when we were figuring out the concentrations of different solutions. And we wanted to figure out what was the concentration of the chlorine anions in that solution. And we know it can be written as magnesium chloride as such, but it can also be split again into an anion and a cation. And we know that there are 2 chlorine ions for every 1 magnesium ion. And we know the charge on each of these thanks to our oxidation state rules. We have a 2+ charge on this magnesium and a -1 charge on the chlorine. Let's consider one more example where we have sodium sulfate, Na2S aqueous. As soon as we throw that in solution, what we actually get are 2 sodium cations that have a +1 charge and 1 sulfate anion that has a -2 charge. So, when we toss in soluble compounds, they can split apart into hydrated ions. But I said in this section we were going to be talking about precipitation reactions. We're going to be forming an insoluble product. So what about insoluble compounds? So what we said, precipitation reactions produce an insoluble product. So how do we know what's going to be soluble and what is going to be insoluble? Well, there are a set of rules that we can utilize to figure out what is soluble and what is insoluble. And these are known as the solubility rules. So what we're going to do now is we're going to go through these solubility rules and try and figure out what will come crash out of solution and what will remain soluble in solution. So, solubility rules. And an important point to make is these rules are followed in order. 1 is followed by 2, followed by 3, followed by 4. We'll figure out what that means in a second. So they're followed in order. very first rule, Rule 1, all alkali. That's the group 1. And ammonium, NH4 plus salts are soluble. So if you have a sodium, a lithium, a potassium, or any ammonium salt, they're always going to be soluble in water. Rule 2, all nitrates, NO3 minus, where the nitrate is the anion. Acetates, C2H3O2 minus. Remember, these are polyatomic ions. And chlorates, ClO3 minus. And perchlorates, ClO4 minus. Those are all soluble. So all salts are soluble. 3, what we have, all silver 1, lead 2, and mercury dimers form insoluble salts. Rule 4, we have most of the halogens are soluble, so chlorine, bromine, and iodine, all Cl minus, Br minus, and I minus salts are soluble. Rule 5, we have a long list of anions, so all carbonate, CO32 minus, oxides, where we have O2 with a minus charge, sulfides, S2 minus, hydroxides, OH minus, sulfites, SO32 minus, sulfates, we'll worry about sulfates later, chromate, CrO42 minus, dichromate, Cr2O72 minus, and phosphates, PO43 minus, are insoluble. Spell that. Soluble. Excluding 4 salts, excluding calcium sulfide, strontium sulfide, barium sulfide, and barium hydroxide. We have one final rule. That's all based off of sulfates, SO4 2 minus, sulfate anion, in which all of them are soluble except a few salts. The final rule, chemistry God saith, rule 6, all sulfates, SO4 2 minus, salts are soluble except calcium sulfate, which is insoluble, strontium sulfate, and barium sulfate. So now we have a list of solubility rules that we can go by. We can actually predict which compounds will be soluble and which ones will be insoluble in an aqueous solution. So that's what we're going to do. Example, predict which salt is soluble and which is insoluble. A, we're going to have potassium nitrate. B, silver chloride. C, lead 2 nitrate. PbNO3 2. And D, sodium sulfate. Now, let's consult the solubility rules. So we have our solubility rules in front of us. What we're going to do, we're going to go through each one of these, and we're going to identify if it's soluble or insoluble. So let's look at potassium nitrate. The very first rule states that all alkali metals are soluble. Potassium is an alkali metal. This is soluble. It is also a nitrate, and if you look at the very second rule, all nitrates are considered soluble. Silver chloride. If we look at our rules and you look at rule 3, it says all silver salts are insoluble. This is insoluble. But you may look at the rule beneath and it says all chlorine anion salts are soluble. But this is insoluble. Remember, rule 3 takes precedent over rule 4. Lead 2 nitrate. If we check out rule 2, again, all nitrates are soluble, so this is a soluble salt. And then for the last one, we have sodium sulfate. If we check through all of our rules, the first one states all alkali metals are soluble. If we look at the very last rule, it also says all sulfate salts excluding calcium sulfate, strontium sulfate, and barium sulfate are soluble. So this salt is also soluble. Okay, so now we know what's soluble and what is not soluble. However, when you write out the precipitation reactions, there's oftentimes a lot of redundant or repeating information. So we're going to now talk about molecular, ionic, and net ionic equations, and how we can try and show the important information while getting rid of all the redundant or unimportant information. So let's now discuss molecular, ionic, and net ionic equations. So the molecular equation is just what we've been doing the entirety of this class. We show everything existing as compounds. So molecular. Show everything as molecular entities. Example, what we have in that case. We're going to look at magnesium nitrate, aqueous, reacting with sodium hydroxide, NaOH, aqueous. And what we're going to get as a product, we're going to get magnesium hydroxide, MgOH2. And then we're also going to get sodium nitrate, NaNO3, because the two just swap partners. The anions switch places, or the partners with the cations. So magnesium will go to the hydroxide anion, nitrate will go to the sodium cation. All right, something's wrong here. This isn't balanced. Let's balance it. We should place a 1 in front of here. marker's kind of crummy. Should have a 1 there, a 2 here, a 1 here, and a 2 here. Now let's go through our solubility rules and predict which one of these is going to be insoluble and which one is going to be soluble. So if we look down our list, we see for the very first one, all alkali metals are soluble. Sodium is an alkali metal, so this guy is aqueous. Let's look through our rules a little bit more. What we can see is for all hydroxides, rule number 5, are insoluble, except that those exceptions. So this is what comes crashing out of solution. All right, so we have the molecular equation. Let's get the ionic. And what you show in the ionic, show everything as ions. As ions, except for the solid that we get, except precipitate. So what we have magnesium as an ion, and we know that it's magnesium 2+, aqueous. We have the nitrates, NO3, -1, they each have a -1 charge. We need 2 of them for each of our magnesiums. So we have 2 of these guys, aqueous. We then have 2 sodiums, so new plus ions that are hydrated. And we have 2 hydroxides, aqueous. We then have our reaction. We form our solid magnesium hydroxide. So we indicate that with a solid. Then we have 2 sodiums, aqueous, and then we have 2 nitrates, NO3, aqueous. All right, so we split everything up into ions, but unfortunately there's a lot of useless information here. There's stuff that's left over. So let's write out the net ionic equation. Net ionic. Where what the net ionic does is it removes all the spectator ions, or the ions that are not important for the chemistry that's going on. So remove spectators from the ionic equation. So we're going to remove those guys. Which ones are the spectators? Well, spectators show up on both sides of the equation. So let's look. Let's see which ones are spectators. So nitrate. Nitrate shows up on the left, and it shows up on the right. That's one spectator. The other spectator happens to be a sodium, because it appears on both sides, the left and the right. So now we can get rid of those. And what we want to just show are the ions that are interacting with one another. So we have magnesium 2+ in the aqueous state reacting with 2 hydroxides, aqueous. They react, and what we get in the end is, again, our magnesium hydroxide, solid. So next time, or next class, what we're going to talk about is we're going to talk about how we can utilize this information and use reaction stoichiometry to predict amounts of solids that will come crashing out of solution.